All right, so you should see the recording icon pop up on your computers, yes? Okay, great. All right, so here is our topics for today. Properties of life, how it's organized, and then sections 4 and 5 from chapter 1. Again, these are in chapter 1 too. I just don't remember what sections they are. So if you have your book handy, you can type it in the chat window and I'll put it up.
Properties of life is 1.2.
1.2?
Yes. And then organization of life is 1.3.
1.3. Thank you so much for those of you that are following along a little bit later. Good morning, baby. Did you tell me your baby's name?
Elijah?
Elijah. I have an Elijah in my family. I will never forget his name. Good morning, Elijah. Buenos dias.
Yeah, I'm just feeding him breakfast. That's why he's...
Well, so he is saying, thank you, Mom. Food is delicious. So first we'll talk about the different properties of life. Now, all living things, they do certain, or they possess certain characteristics so that we know that they are actually alive. We can't always tell that something's actually alive just by looking at it. And so scientists have come up with a list of characteristics. Sometimes you'll hear that word used too. A list of characteristics, yeah. A list of characteristics or a list of properties that something has to exhibit in order to be considered alive. And if you want to be alive, you have to exhibit all of these properties, not one or two, but you have to demonstrate all of these. So you have to be able to do all of these to be considered a living thing. Some of them are very visible, I mean, like we can look at you and see it happening, and others are more hidden. So for example, one of the things that you have to be able to do in order to be alive is you have to exhibit some sort of metabolism. Some parts of metabolism are hidden, some of them are more obvious. Now, metabolism means that you basically take in food and you process it. And the processing is both you break it down and then you absorb it. And then you may even rearrange your food. Rearrange the parts of your food in order to make what you need. So for example, some of you have very lovely long hair. It's been a while since I've had long hair, but your hair grows a little bit every day. And in order for your hair to grow, you have to take in food. And so what you actually do when you take in food is that you digest that food, you break it down, you absorb it, and then you rearrange the parts of your food to make things like your hair. So metabolism is more than just eating, it's taking in food and it's processing it. We can sometimes like see something eating, but we don't actually see you digesting it inside of your body, and we don't see you absorbing it inside of your body. That's kind of a hidden sort of thing. But most of the time we can see you taking in food. Eating is sometimes visible, but digestion is invisible itself. But kind of what tells us that digestion is happening is the generation of waste products. Metabolism is not 100% efficient. When you take in food, you're always going to have some stuff left over that you can't use. And so we can tell that you are digesting because you produce waste products. Some examples of waste products probably won't surprise you. Water. Things like, of course, urine, which is mostly water, but it's got some other stuff in it as well. And in some case, organic waste matter, or what we call feces, those are obvious waste products. But things that you might not consider to be waste products are things like carbon dioxide. Or if you're certain types of bacteria, what we call methane. In some cases, like plants, oxygen is a waste product. And the most common waste product on the whole planet is heat. So if something is undergoing digestion and absorption, and if it's rearranging things inside of it, then these are going to be produced. So even if you can't see something digesting, you know that it's digesting because of the waste product that it's produced. So living things have to take in some food, they have to process it, and they're going to give off a waste product as part of that metabolic activity. Okay. Another thing living things must do is what their metabolism supports, and that is they usually exhibit some amount of physical growth. In other words, living things usually start out small, but over time, they're going to get bigger. Along with that, they're also going to develop. And development is a process of maturation. So not only do you get bigger in size, you also mature as you are getting physically larger in size. And so maturation means that you do things at different stages of your life. How many times have you heard of, there are life stages, or you can think of stages of development in your life? So for example, if you're a baby, most babies can't walk. Okay, they can't do that. Not until they reach the age of somewhere between 9 and 12 months are they physically able to walk. Different babies start walking at different ages, but it is normal, okay, it is normal for babies to start walking somewhere around the age of 1 year old. If a baby's not walking by the age of 1, or at least trying to walk, then we might say there is a developmental delay. Have you heard of that term before, a developmental delay? So if not at least trying by 12 months, then that might indicate that there's some sort of a developmental delay. That doesn't mean it won't happen. It just means that for some reason, that baby is not showing a stage of physical maturation that it should be showing. Sometimes delays can be made up. So you're not walking by 12 months, but by 13 months, you're walking and you're running. So it's not a steady progress always. Maturation is a little bit different for every living thing, even amongst humans. Not everybody gets their first tooth by the time they're 4 months old. Sometimes babies, their teeth don't start coming in until around 9 months old. And the same thing for a little bit older. When you think about the onset of puberty, all right, boys start getting, hair on their chins, their bodies start to change. The same thing for girls. They start to develop. You start to see fat distribution so that they have the development of like curvier shaped bodies. They have hips, there's development of breasts, they begin their cycles, their menstrual cycles. Not everybody begins those things at the same age. But if humans are not showing signs of puberty by the time they're 15 years old, that's an indication of a developmental delay. It's also possible that maturation happens too quick. And since we're using people as an example, there's something called precocious puberty. There's something called precocious puberty. And precocious puberty means that basically it's happening too soon. It's happening too soon. There's a study over, I want to say, the last 25 to 30 years that indicates in humans, especially girls, puberty is happening younger and younger and younger. If you look at medical data from the last, at least 100 years, most girls did not start their menstrual cycles till somewhere around the ages of maybe 12 to 14. Now we're seeing evidence that girls are starting, on average, their menstrual cycles as young as the age of 10. And in some cases, even 9 or 8 years old. That's crazy. That's evidence of precocious puberty. It's happening much younger than what we would normally expect. Now, what is the reason for that? There's lots of possible hypotheses as to why that's happening. Some people blame the hormones in our foods, like the hormones in milk, and things that can delay it are like stress. Girls that grow up in countries where there's constant wars are more likely to delay their onset of menstrual cycles, whereas girls that grow up in countries like the United States, where food is rich and plentiful but full of hormones, are more likely to experience it at a younger age. And so we know that metabolism influences both physical growth and, to some extent, the development or the maturation of living things. The idea is that both metabolism, growth, and development, they should all happen together at just the right time. So physical growth, let me put this real quick, increase in size. But development is more of a maturation process. So even these first properties of life, you can see that the idea is that they have to happen in concert with one another. In other words, they have to happen at the right time. So that brings me on to my next idea of living things. Is that living things have to exhibit what's called homeostasis. This is a Latin term which literally means stay the same. Literally means to stay the same. Homeostasis, this is not a thing that I can point to, but it's an internal set of conditions that basically that living thing tries to regulate. You can think of your homeostasis as kind of like being your overall measure of how healthy you are. Okay. How healthy am I? And your ability to remain healthy means that you have to regulate those internal conditions. So some things that relate to your overall health or your overall homeostasis is like your ability to regulate your blood sugar. The ability to regulate your blood sugar levels. I'm curious, you can give me a thumbs up. How many of you watched my flip grid? What? Okay, Leah did. How many of you watched my flip grid? I poured my heart and soul into that flip grid video, people. My heart and soul. But one of the things I mentioned in my flip grid video, which was answering why do I think the study of biology is important, was I said that one of the things that impacts just about everybody in one way or another is diabetes. We either know somebody, or we might live with somebody, or heaven forbid, we ourselves have diabetes, or maybe we've been told that we're pre-diabetic. In some cases, it's even possible to be diabetic for a temporary amount of time. This happens a lot with women who have babies that are pregnant. Sometimes they develop diabetes when they're pregnant, and then after their baby is born, they don't have diabetes anymore. But I like to call diabetes the Campbell's soup of diseases because of a study that was done several years ago. They said that the Campbell Soup Company, they make more than just Campbell Soup, but the Campbell Soup Company, they have 100% consumer penetrance in homes. That means that every single person in the United States has some product in their homes right now that was made by the Campbell Soup Company. I've got cream of chicken all over the place because I never know when I'm going to make some sort of creamy chicken enchilada sauce. I've got, chicken noodle soup. I've got chicken broth. I am a well established example of the 100% consumer penetrance. In my opinion, diabetes is kind of the same way. 100% of the households in America either know someone or they have someone that either is impacted directly by diabetes or they've been told they are possibly pre-diabetic. And so diabetes is basically a situation where it is a challenge to regulate your blood sugar level. This is a hormone problem. So this is a situation where hormones are just not working the way they need to be working so that blood sugar levels are well regulated. Now, when your homeostasis is interrupted, it doesn't necessarily mean that you're going to suffer to some great extent. Because if I use blood sugar level as an example, most people's blood sugar level is somewhere around 100 to 140 when they have been fasting. So if you go to bed at night and you don't wake up until the next morning and you've been fasting for about 8 hours, the average person, their fasting blood sugar level is somewhere around 100. 100 is around 100. That's after an 8-hour fast. After you eat, your blood sugar level may climb as high as 140. So within 1 hour of eating. Okay. And so for somebody who's not diabetic, it's possible that their blood sugar level goes all day long between 90 to 140, depending on how often they're eating and when they're eating. That's completely normal. That's not a problem. That's not a problem. But for the person who is diabetic, these numbers are not within an acceptable range. So this 90 to 140 for a non-diabetic under normal conditions is totally okay. Okay, totally okay. But for somebody who's diabetic, their blood sugar levels exist outside this range of 90 to 140. Sometimes in the morning, somebody who's diabetic, their blood sugar level may be as low as, let's say, depending on the type of diabetes that they have, maybe it goes down to 85. That's too low. Or somebody who's diabetic in the morning, their blood sugar level is much higher than what it should be. Let's say it's 180. That's too high. So after an 8-hour fast, having 85 to 180, that's too high of a range. Sometimes diabetics, after they eat, their blood sugar levels can go as high as 300. That's scary high. That's scary high. So people who have diabetes have a hard time regulating their blood sugar levels, and they have to do so by either watching their diet or taking medication or using insulin. They do something to regulate those blood sugar levels. The acceptable range of 90 to 100, that's an example of your homeostasis. That's totally normal, and it's not unusual for somebody's blood sugar levels. Even if they are diabetic, it's not unusual for their blood sugar levels to have that wide of a range. But if you go far too beyond, either too low or too high, then the body begins to suffer. The body begins to suffer. So depending on how low or how high, you suffer in different ways. People whose blood sugar is far too low, they might feel weak, they might feel shaky, they'll definitely feel hungry. And people whose blood sugar is too high, they may feel dizzy, they may feel nauseous. They know that something is just not right. Even people who are not diabetic, when our blood sugar levels gets to about 90, we start to feel hungry. Our appetite is stimulated. So the corrective measure that happens when your blood sugar gets too low could be sometimes that you stimulate your appetite. It could also be that there's a hormone response to help you raise that sugar level. And consequently, when it gets too high, there's also a hormone response to lower your blood sugar levels. Not only is the signal to eat part of your homeostasis, but the hormone signals that change your blood sugar levels, or at least try to change them, those are also part of your homeostasis. So again, it's kind of hard for me to just point to your homeostasis. I can't say there it is, because homeostasis isn't just one thing. It's all of those internal conditions, but I'm going to add to that, and the processes involved in that regulation. Blood sugar levels, it's just one example of your homeostasis. Other examples could include things like your body temperature, your blood pressure, even how acidic or how basic your blood is, your blood pH levels. Okay. Things like your breathing rate. It sounds crazy, but if we think back to this idea of metabolism, even waste output, those are all part of your homeostasis. Everything that your body does to keep you within acceptable levels. Or you can think of it, all the things that your body does to help you maintain your health. It is possible to go outside your normal ranges and you can recover, right? If you get hungry and you eat, you recover. If you get hungry, you don't just lay down and starve and that's it. I give up, I'm hungry, I'm done. No, you do something so that you recover. But it is possible to go too far outside of your homeostasis and your recovery is limited, or if you stay too far for too long, you don't recover. So it's possible to recover either fully or to a limited capacity if you stay too far outside the range. But also know that if you stay too far outside for too long, then it's possible that you can't maintain it and your systems don't recover. I know we use this expression sometimes, oh my gosh, I'm starving to death. But are we really? Most of the time we're not. It's a temporary feeling. Starving to death takes a really long time. Takes a really long time. It's not something that happens within an 8-hour period. Each one of your homeostatic examples has a different level of tolerance. Has a different level of tolerance. Starving to death takes a long time. But if you stop breathing, how long does it take to die? Minutes, right? Minutes. You won't die from starving to death within minutes, but if you hold your breath and never take in another breath, it doesn't take that long to stay too far outside of your homeostatic levels. Give me a thumbs up or ask me a question. Give me a thumbs up if you're good with homeostasis, or ask me a question.
So with staying inside the normal ranges, so if you got like 107 body temperature and fried your brain, that would be like being way too far out.
Oh yes, 107 Fahrenheit is too far out. It may not mean death, Shane, it may not mean death, but it will definitely cause brain damage, and it may be irreversible brain damage. That's why doctors are real concerned with high fevers. High fevers for a long time can cause brain damage. Sometimes we don't even see the brain damage immediately. Sometimes it might take a couple of years before we see evidence of the brain damage. And that kind of goes back to the idea of development. So if you are, 5 years old and you have a high fever for a long time, you might have some brain damage, but we might not see it for another month or maybe another year. In some cases, if the brain damage is significant, we'll see it right away.
All right, sounds good. I was just trying to clarify, making sure I was on the right track with that.
Yes, you are. Excellent. All right, so give me a thumbs up if I can move on to the next property. All right, good. So we're on number 4, right? We're on number 4. So besides metabolism, besides homeostasis, there's another property of life that I alluded to a while ago when I said things have to happen at the right time, at the right place, or at the right pace. Things have to be coordinated. All of the processes, and you can think about this as, your homeostasis, all of the things that happen in order for you to be healthy, they have to happen at the right time and at the right place. So events have to happen not only at the right time, but also at the right pace. So they can't happen too fast, they can't happen too slow, and they have to happen at the right time. If something interrupts all of this, you have to have the ability to correct it. You have to have the ability to correct interruptions, and that ability is called irritability. So you have to be able to coordinate these processes so that they happen, again, at the right time and at the right pace. And if there are interruptions, then you have to be able to correct those interruptions. So Shane, using your high temperature example, you can't let your body temperature continue to climb. Even if it's not because you're sick, maybe you're just outside playing basketball, or maybe you're outside gardening. You can't let your body temperature continue to climb. So what your body does under normal conditions is that you perspire. and that's to cool you off. So that perspiration, it has to come at the right time. It has to come at the right pace, or I guess I should say at the right intensity. It's got to cool you off in order for it to work. The same thing as if your body temperature drops too low, you may shiver in order to generate heat. So living things, they have to have this irritability, which is part of coordinating all of those processes inside of them. Sometimes we say that living things have to have the ability to respond. I don't remember what your textbook says exactly, but if you go to other websites, sometimes they describe this as the ability to respond, but definitely irritability is part of it. Living things have to have the ability well, let me say it this way. Living things have to have the ability to pass on their genetic information. Now, all living things, they use as their genetic information good old DNA, which is an abbreviation I'm sure most of you know, but DNA is an abbreviation for the term deoxyribonucleic acid, that gorgeous molecule that looks like, you know, a twisted ladder. Living things have to have the ability to pass on their genetic information. Now, they can pass it on a couple of ways. They can pass it along asexually, which means you have one parent that generates one offspring, and they are clones of each other. That means that the DNA remains unchanged. An example in people of an asexual process is mitosis. Mitosis means that your cells divide for the purpose of cell replacement and also for physical growth. So mitosis is cells making more cells so that you can replace cells that either get old or they get injured or you lose them because maybe you got a cut and you bled a little bit. But also if you're going to get physically bigger, you need those cells to get physically bigger. So in mitosis, you have one parent cell that literally divides in half, and you have two daughter offsprings. So right now, you are undergoing asexual reproduction in the form of mitosis. You're doing it in order to replace any cells that you have that got old or to support physical growth. There we go. All right. Passing on your genetic information can also be sexual. And if there's any part of this list that I could say, I guess, is optional, this is it. Passing on your DNA sexually is optional. In other words, you don't have to exhibit this in order to be alive. Everyone has to have some sort of asexual reproduction for cell replacement. But sexual reproduction, where you have two parents to produce an offspring, and the DNA is what we call recombined or changed. This is a whole optional area of a property of life. So having babies is not a requirement for you to be alive. I don't have any babies, but I'm just as alive as those of you that do have babies. Now, I will say that Mother Nature does want you to make babies. She puts a lot of, how can I say this delicately? She puts a lot of processes for us to be encouraged to make babies. Some of them physical, some of them psychological. But Mother Nature wants to encourage us to sexually reproduce for the point of passing on our DNA. And in this case, in large-ish populations. Asexual can be an internal process. This is more outside of just the individual. Mother Nature wants you to pass on your DNA so that it really gets out there. So if I need a diagram, we have two parents fusing to make one new offspring. This would be the sperm. This would be the egg. So you might see this on a quiz. What's the only kind of exception to the rule that you have to demonstrate? What's the only exception to the rule of things that you can omit and still be alive? And that would be to sexually reproduce offspring. You don't have to do this in order to be alive. But if you are a multicellular organism, you have to do this in order to be alive. You have to. Speaking of cells, that's our next one here. Living things have to be made of cells. There's this idea called the cell theory. 3 statements. And the first part is the cell is the basic building block of life. In other words, nothing smaller than a cell exists. The cell is the smallest thing that can demonstrate all of the properties that we're talking about. So it's the smallest thing that can demonstrate, I'll say the smallest entity that demonstrates all of these characteristics or all of these properties. The second statement says all living things are made of, you guessed it, cells. Some living things are only one cell big. They're unicellular, like for example, all bacteria. Bacteria are only one cell big. But then you and I, we're made up of many cells. We are multicellular. So all living things, regardless of what they are, they're either going to be one cell big or they can be many cells big. They can be one cell big or many cells big. But the idea is that living things are made of cells because that's the smallest thing that can demonstrate all of the properties of life. The last part of the cell theory kind of answers the question, where do cells come from? Well, they come from pre-existing cells. That goes back to this idea of passing on your DNA. Cells reproduce. They come from other cells. This does not answer the question, where did the first cell come from? That's a whole different question. This is just saying, where do cells come from in general, or they come from other cells? Because cells will reproduce, either sexually or asexually. They'll reproduce. The last characteristics of living things. Oh, I've got two more. They exhibit organization, which that's part of our theme coming up, but they have parts to them, or they have components. They have parts or they have components. They also are part of a hierarchy. I'm going to skip this for now because that's a little bit more detail that I'm going to share with you probably next time I see you. But the last one I want to talk about is living things change, or we can say that they evolve. Well, let me do it this way. They adapt and they evolve. Living things have the ability to change, or they adapt and they evolve. Adaptation is something that we see in the individual, whereas evolution is something that we see, it's a change in a group over time. Okay. So adaptation and evolution, what they have in common is that they are both changes. But adaptation happens in the individual, and evolution happens in a group, and it happens over a period of time. So these 8 characteristics that I have listed, if you go to your textbook or if you go to other websites, they may list these in 4 big groups. They might list them in 6 groups. They might list them in 8 groups. It kind of depends on who the author is, how many items they put on their list. So it doesn't matter, like I mentioned, if I make a list of 8, or if you go online and you see a list of 6 or a list of 5, these characteristics are still considered to be all examples of things that you must exhibit in order to be a living thing. You have to do all of them, with the exception of sexual reproduction, but you have to do all of them in order to be considered a living thing. You can't just do most of them, you have to do all of them. The last little thing I'm going to talk about today, I have just enough time, is talk about how living things are organized. I mentioned in our list that they exhibit organization, and that's the last thing I'll talk about today. Next time I see you, I'll talk about the themes and some unifying ideas. So last thing for today, what do we mean by living things exhibit organization? I guess I should have put a box around this. Living things are organized. There is an internal organization, but there also is what we call a hierarchy. Internal organization, this is exhibited in the individual. So we can say, for example, you are organized because you have organs. You are also organized because you have cells, and each one of your cells have cell parts. Those are things that, you know, if I were to open you up, I could see that you have parts to you. And even at the very most tiny level, even your cells have little parts. Even if I can't see them with the naked eye, you still have parts. Hierarchy means this is a level of organization like where you belong versus other organisms, or how your parts relate. That's the difference. And once I give you the hierarchy, you'll probably get it. You'll probably get it. So, for example, the smallest living thing that can exist, we said earlier, is a cell. That's the smallest living thing that can exist. But cells themselves are made up of smaller parts. Parts that make up a cell are referred to as organelles. Some examples of organelles, you may have heard of these before, but like a nucleus, or my favorite, the mitochondria. If we're talking about plants, maybe the cell wall. Those are parts of a cell. These individual things are not alive, but they constitute a living thing. Organelles themselves are made up of smaller parts. They're made up of things called organic molecules. And I know you've heard of some of these organic molecules. So some examples of organic molecules are things like carbohydrates, or maybe fats. Carbs and fats are not alive, but they constitute cell parts, and cell parts make up cells. Organic molecules themselves are made up of atoms. So they're made up of things like carbon and hydrogen. Carbon's not alive, hydrogen's not alive, but when they combine in certain ways, they make up smaller or larger components, which in turn make other components, which in turn make up something that's alive. This right here is an example of a hierarchy. This is a hierarchy. We can keep going with our hierarchy here because cells themselves can organize into tissues. So examples of tissues might be something like connective tissue, or maybe even muscle tissue. Tissues in turn can be organized, I'm running out of room, into organs. So like your heart, your skin, and then organs are organized into organ systems. And then organ systems, oh my goodness, I'm gonna have to turn my paper sideways. Systems themselves are organized into multicellular organisms. If you are unicellular, your organization stops right here. If you're unicellular organisms like bacteria do not make up tissues, organs, and multicellular organisms. You and I do. You and I do. We make up multicellular organisms. So you and I have organs, we have tissues, but bacteria don't have muscle tissue. Bacteria don't have a heart. Bacteria don't have a cardiovascular system. If you're unicellular, your hierarchy stops here. But if you're multicellular, your hierarchy continues. So far, so good? Give me a thumbs up because I've got one more thing to show you, or one more thing to tell you about hierarchy. Here's the last thing. We can also have a hierarchy with organisms themselves. Okay. We can also have a hierarchy with organisms themselves. So for example, you can have a living thing, whether it's one cell big or many cells big. And if you have a group of them that can reproduce, they're called a population. So again, a population is many organisms of the same type that can interact, and they can breed. They can reproduce to make more of their kind. If you have two or more of these, then you are called a community. So two or more oh, I guess I don't need an apostrophe. Two or more populations, and they've got to be at a particular location. So you've got a group of birds and a group of turtles out at bottomless lakes. And then two or more of these, two or more communities, can constitute an ecosystem. And then all the ecosystems on the whole planet are located in the biosphere, or sometimes we refer to them as a biome. Many ecosystems. So for your next quiz, be able to make up this hierarchy all the way down from atoms. I ran out of room on my paper. Where did I put it? Here it is. So be able to recreate this, or at least explain it all the way down from atoms. Yeah. All the way down. So this could be either single-celled or multi-celled. I'm finishing up a little early today, so I have time for any repeats or if you have any questions. I'm gonna go ahead and stop recording, but before I do, the next time I see you on Thursday, we're gonna pick up right here, section 4, some themes in biology and some unifying ideas. So some themes and some unifying ideas. And I'll probably also work in a little bit of types of living things. I'll probably do that as well next time. But I'm going to stop recording, and then I'll use the rest of my time to answer your questions.